Hi, and welcome to the Thermodynamics Podcast Part 2. In this podcast, we're going to talk about determining the sign for entropy. Now, if you wanted to actually calculate entropy, you could do it in a very similar way that we calculate delta H or enthalpy, where you would be given a series of entropy values for each reactant and each product, and you could do the sum of the, hold on, I'll draw that a little bit better here. You could do the sum of the sum of the products minus the sum of the reactants, and that would give you your change in entropy. Most delta G problems, though, that we're going to solve, and delta S problems we're going to solve, you just have to actually figure out the sign for entropy, whether it's positive or negative. So, entropy is a measure of disorder, and the universe in general tends to favor disorder. So the whole universe is increasing in entropy. And so if you have a positive delta S, it is more disordered. And if you have a negative delta S, it would actually be more ordered. So if you kind of think about it, I don't know how your household is, but we start out Sunday with our house all perfectly straight, clean, neat, organized, right? And then by Friday, the house is kind of a disaster. And then, so basically during the week, it's got a positive delta S because kind of just goes to chaos, and we leave papers out on the counters and we need to file things away. And then it gets to Friday and we have a negative delta S where we go through and we clean everything, we put it away, and we get everything back to where it is. So some examples of increasing entropy. Again, increasing entropy has a positive delta S. It's really important to know the signs, which direction they go. So going from a solid to a liquid increases entropy because a solid is the most structured. It has the strongest bonds. They're not moving very much, the molecules or the ions or the atoms in the solid. And it's going to be very, very organized, right? So that's going to be very, very, or solid is very, very organized. And then, of course, going from a liquid to a gas, anytime you form a gas, that's going to have the most entropy because gases basically are just going in every direction that they want. They're just bouncing off of things. They're flying around. This is my gas. It's just going everywhere that it wants to go. It has complete freedom of motion, as opposed to a solid that has to stay in its solid form. It's really not moving around very much. Number one and number two kind of go along with each other. If you're starting with, let's say a solid, and you form a gas, you'll be increasing the number of moles of a gas down here at number 2. Or if you start with a gas and then you break it up into more moles of a gas, so if you start with like 2 moles of a gas total, you make 4, that would also be increasing entropy. Basically, anytime you make more gas or a gas, that is going to be a positive delta S. Another way is by dissolving liquids or solids. We mostly want to think about this with solids. So if you have a solid, and I drew it over here like a sugar, a salt cube. You have a perfect crystalline lattice. You have an Na, then you have a Cl minus, Na plus, Cl minus. Okay, and it's just going to keep alternating, and you've got that in an entire cube shape. So I kind of have that thrown there. When you add this into water, what's going to happen is it's not going to have that perfect cube shape. Instead, it's just going to have Na pluses and Cl minuses kind of floating around, moving every different direction. So you've increased its freedom of motion, and if it's allowed to move around more, then it's less ordered. Okay, so that's going towards more disorder, which would be a positive delta S. With the dissolved, right? So if I'm dissolving a liquid or a solid, this would not work with gases. It's actually the opposite with gases. So if you start out with gases that are kind of trapped in a solution, so for example, NH3, when it's trapped in solution, becomes NH4 plus. If we add NaOH into the solution, that will react with this and form NH3 gas. And we know that anytime we form a gas, that would increase entropy. So then this would bubble off, the gas would escape. You can also think about this in terms of carbon dioxide when you have carbonated water. So when you open the carbonated water, the bubbles start to escape freely on their own and going out back into the air. So a dissolved gas is going to just a gas that's free in the air would be increasing in entropy. The last one is a little bit tricky. You're going from smaller molecules to larger molecules. So if you're comparing, let's say like CH3, so that would be, that's the carbons, and these little dashes just represent hydrogens. I'm not going to draw them all in. And then you're going to compare that to, let's say, CH6, hexane. The thing is that it's very hard to compare these because the propane at room temperature is much more likely to be a gas. So a lot of times they're going to have more entropy, because the smaller molecules actually, because they're going to be in the gas form. But let's pretend that we have both of these as liquid. So I have the propane, the C3 as a liquid, and I have the hexane, this one, as liquid. So if both of them are liquids, then this one down here actually has a higher level of entropy because it has more freedom of motion. So the larger the molecules get, the more that they're going to be able to move, twist, move around, because each one of these bonds, the carbons can rotate around one another, and so it just gives freedom of motion. You really, really, really have to be careful though with this rule, because if you have a smaller molecule and it's a gas, and a larger molecule and it's a liquid, which is what you would have at room temperature, this then would have more entropy, because being a gas is a much higher level of entropy than the size of the molecule. This mostly comes into play with very large biological or biochemical molecules. And so basically it just goes to show that if you have a really large molecule, it's going to be a little bit more disordered, because there's different ways that the molecule can move around, or different bonds that can break and reform. So this mostly has applications to biochemical molecules. Okay, and in the next podcast, I'm going to show you how you can apply delta H, which is enthalpy, and then a delta S, which is entropy, to the Gibbs free energy equation.